Hey class, welcome back to Behavioral Statistics. We are going to jump into chapter number 8 on our introduction to hypothesis testing. Really, this is another way of thinking about this is we're really doing an introduction into inferential statistics. So here are the learning outcomes, things that you should be able to do by the end of the chapter: understand the logic of hypothesis testing, state the hypotheses, and locate critical regions on that normal distribution, conduct a z-test and make a statistical decision or make a decision about your, results from your statistic, define and differentiate type 1 and type 2 errors, understand effect size and compute Cohen's d, and make directional hypotheses and conduct a one-tailed test. The things that you'll be using from the previous chapters that we've covered: z-scores. We're going to be calculating a z-score as part of our first hypothesis test. We'll look at the distribution of sample means, so expected error, standard error, probability, and sample means. So nothing new as far as tools that we're going to be using, but we're kind of reframing it in terms of inferential statistics. So, kind of the logic behind that first learning outcome. This is one of the most common ways in which we use inferential statistics. And really, what this is attempting to do is using our sample data to evaluate our hypothesis about a population. So, we are researchers, scientists are interested in populations. They cannot collect the data from populations from everybody. So, what they do is they have a hypothesis, they draw a sample, and go from there. And based on the data, what kind of how do we evaluate that hypothesis? So we're going to be looking at kind of the logic behind that. You want to state your hypothesis. Researchers will state their hypothesis about a population. This is their educated guess. It's not a random guess. It's usually backed by some kind of previous research, theory, or some kind of, there's a logical reason for why the hypothesis is usually stated the way it is. And it's attempting to describe the characteristics of the sample based on the hypothesis. Usually it's drawn. Hopefully, we're using random samples at this point, and we're comparing the obtained sample, the random sample, with the prediction that was made based on the hypothesis. If it's consistent with our hypothesis, then we presume it's reasonable. If there is, however, some kind of discrepancy, which we'll pick up, in the statistics, then we reject this hypothesis. So typically, we have maybe some kind of known population. We maybe know some factors about them, mean and standard deviation. We want to run some kind of treatment. Perhaps maybe since we're talking about psychology, it could be new medication, it could be new form of therapy, it could be some kind of intervention. And then we want to know maybe what are the population statistics after treatment. And we want to know, is that statistically significant, essentially, is what we're getting at. So perhaps we have our known population, we pull a sample, we use the treatment, we collect the data from the treated sample, and we want to compare that to the original population and see, is there some kind of statistically significant difference? So some of the steps involved in hypothesis testing is: one, state the hypotheses; two, set the criteria for a decision; three, collect data and compute sample statistics. And really, from here on out, we're going to be looking at different ways that we can compute those sample statistics to make decisions, based on our hypotheses. So in psychology and other, forms of research and scientific research, you start with what's called a null hypothesis. It's stated with H0. And really what this null hypothesis is saying is there is no effect. There's no change. There's no difference. There's the independent variable in this case has no effect on the dependent variable. So really that's where we're starting from. We're starting from this assumption that there's no difference, versus we also have the alternative hypothesis, H1, states that there is, in fact, some kind of change or difference or relationship for the general population. So really scientists are working from is we're starting with the null hypothesis, the assumption that there is no difference. We set the criteria for the decision. And this is in terms of what kind of alpha level we'll look at. We'll talk about that later on, your level of significance. Looking at a distribution of sample means is then divided into two sections: those that are likely to be obtained if the null hypothesis is true, and those that are very unlikely to be obtained if the null hypothesis is true. And again, we're setting that alpha level or significance level, and that's our probability value to define what is very unlikely in a hypothesis test. And typically the rule for most research is 0.05. We're setting an alpha level of 0.05, or a probability value in this case, 0.05 or 5%, that we're defining as very unlikely. So here's another way of looking at it, knowing what that 5% value. If our results occur 5% or less of the time due to chance alone, we consider our results improbable due to chance alone. Something else is likely responsible for the presence of our results. In this case, a true difference or a true relationship in the population or a true treatment effect. So we can say that our results are statistically significant. We reject the idea that there are the results of the chance alone. So when we say something is statistically significant, we are rejecting that null hypothesis. We are saying there is something going on there. There's some kind of difference happening. That's the kind of way you have to kind of start thinking about these things. Step two, we define those critical regions. Those consist of extreme sample values that are very unlikely to be obtained if the null hypothesis is true. We set the boundary for those critical regions. They're determined by the probability set by alpha level. And so if the sample data, and this is where we start getting into like the hypothesis testing, if our sample falls in those critical regions, the null hypothesis in this case is rejected. If the critical value, if our sample data falls within those critical regions, then we're talking about we're failing to reject or we're retaining the null hypothesis in this case. And this is what I mean. So we have these extreme low probability about. Remember, in a normal distribution, most of the data is going to kind of collect towards the middle. Things that happen on these left and right ends are from a probability standpoint, less likely to happen. So we're talking about low probability values if our null hypothesis is true, high probability values if the hypothesis is true. So if our sample statistic comes back and we're getting values in either one of these critical regions, I'll show you how to do that later on, then we are going to reject the null hypothesis. We are saying there is something happening there. So these are those critical regions, and it's a really good point for when we talk about a two-tailed test is what we're talking about now. We set our alpha level at 0.05. We divide that up in half, 0.025 on each tail, and the critical value is going to be 1.96 on both sides, negative 1.96 on the left-hand side, positive 1.96 on the right-hand side. So already you really need to have those numbers down and understanding like if we run our our z-score test we're going to look at later and that value is higher than 1.96, we reject the null hypothesis. If it's less than 1.96, like it's in this, if it comes up in this region, then if it's between negative 1.96 and positive 1.96, then we retain the null hypothesis or we fail to reject in this case. Okay, let's do a quick learning check. Sports coach is investigating the impact of a new training methods in words. What would the null hypothesis say? A, the new training program produces different results from the existing one. B, the new training program produces results similar to the existing one. C, the new training program produces better results than the existing one. Or D, there is no way to predict the result of the new training program. Go ahead and pause the video here. Think about it, come up with your answer, write it down, come back when you have an answer. Okay, in this case, the correct answer is B. They're the same. There's no difference, essentially, is what we're saying between if the null hypothesis. And the null hypothesis is going to say there's no difference. We're starting from the point that there's no difference. Next one, true or false. If the alpha level is decreased, the size of the critical region decreases. And the next one, true or false, that the critical region or the critical region defines unlikely values if the null hypothesis is true. Go ahead and pause your video here and come back when you think you have an answer. Okay, both are true in this case. True, alpha is the proportion of the area in the critical region. So if we are decreasing alpha, the size of our critical region is also going to decrease. So if we decrease our size from 0.05 to 0.01, for example, we're going to get a much smaller region, rejection region. And then true, this is just the definition of unlikely. I know it's kind of stoically worded, but that's what we're working with here. Then we want to step 3 now. We're going to collect data and compute sample statistics. So data are always collected after the hypotheses are stated are null and are alternative. Data are always collected after establishing the critical region or criteria for, for a decision. So to determine what your alpha level is, and this is attempting to assure objectivity, a more honest evaluation of your data. So we can compute a sample statistic, in this case, a z-score, to show the exact position of our sample. And remember that all we're doing is using that equation from the last couple of chapters, finding z-scores for a sample mean distribution. So in other words, what we're doing is the z is the difference between our observed sample mean and our hypothesized population mean divided by the standard error. So we're not doing anything different than what we did last chapter in chapter 7. And then we make a decision, we obtain the z-score, and we make a decision. We have two possible outcomes. We retain the null, or we fail, or we excuse me, we reject the null hypothesis, or we retain the null hypothesis, depending on how you want to phrase that second one. The sample data are located in the critical region. We reject the null hypothesis. So if it's in those tail regions, the 1.96 values we talked about in a previous slide, the sample data are not located in the critical region. The data do not provide strong evidence that the null hypothesis is wrong. So in this case, we fail to reject the null hypothesis. So the null hypothesis is either rejected or the researcher fails to reject the null hypothesis. So this is our analogy, kind of using a jury trial in this case. So the process of conducting hypothesis is similar to a jury trial. You're starting from the null hypothesis that the person is not guilty. They are innocent until proven guilty, and it's up to the police and prosecutors in this case to gather evidence, or data. If we're talking about statistics, they're gathering data to test whether the accused actually did they really commit the crime. With sufficient evidence against the defendant, the jury then rejects the null hypothesis of innocence claim to conclude that the person is in fact guilty. With inefficient or insufficient evidence against the defendant, the jury will fail to find the defendant guilty. There's just not enough evidence, but doesn't necessarily conclude innocence, but just says, hey, you're not guilty. We don't have enough evidence to convict. So that's kind of an analogy of a way of thinking about that. So looking more at that z-score statistic, it's just a ratio, the actual difference between the sample mean and the hypothesized population mean divided by the standard error between m and our population mean. So a sample of z-score of +3 means the obtained difference is 3 times larger than what we would expect if the treatment had no effect. We're really venturing pretty far out there past the critical region in this case. So, quick learning check. True or false, when the z-score is quite extreme, it shows that the null hypothesis is true. And second one, true, false, a decision to retain the null hypothesis means that you proved the treatment has no effect. So, pause your video here, make sure you understand both of these before moving forward. All right, both are false. First one, an extreme z-score is in the critical region, thus very unlikely the null hypothesis is true. Second one, failing to reject the null hypothesis does not prove it's true. There's just not enough evidence. It's going back to that idea of like, just because you're proven not guilty doesn't necessarily mean you're innocent, just means we don't have enough evidence to prove you're guilty in this case, or the prosecution, I should say. So now we're looking at their idea of there's errors. Remember, we are making inferences. We're making inferences from samples to population. So we're going on limited information, just the data that we have to make a statistical decision. Sample data is used to make those decisions, to make inferences. But, of course, there are errors that are possible. We even talked about that last chapter with our standard error equation going from sample error or sample to population to sample. So errors are possible. So the two that we're going to focus on for this chapter are type 1 errors. The first one, type 1 and type 2. So type 1 is when the researcher rejects a null hypothesis that is actually true. The researcher is concluding that a treatment has an effect when in fact it does not have an effect. So the alpha level is the probability that our test. So really what we're talking about with alpha is, will this lead to a type 1 error or not? It's determining the probability of obtaining a sample data in our critical region even though the null hypothesis is true. So we're falsely rejecting the null hypothesis with a type 1 error versus a type 2 error. The researcher fails to reject a null hypothesis that is actually false. So the researcher has failed to detect a real treatment effect. The sample mean is not in the critical region, even though the treatment has an effect on the sample. So, and this is kind of a different, the probability of this is a little bit different in terms of, but the most kind of recent example I can think of with type 1 errors is like whether or not people should wear a mask when it comes to prevention. So, type 1 error in this case, prevention of like spreading infectious diseases and illnesses, flu, COVID, things like that. Type 1 error would be wearing a mask, even though, it doesn't help, essentially, is what we're saying. We're saying it has no effect, but yet I'm still wearing this mask, but it's not going to prevent anything. And so, really making a type 1 error in this case, like, you wear a mask and maybe even if it doesn't hurt, whatever, not a big deal. Maybe people kind of give you some weird looks or whatever. But type 2 error is a little more consequential. This is when we are, so we're failing to reject our null hypothesis. We're telling people in this case, maybe you don't need to wear a mask when in fact it would actually prevent. So, and that's kind of, so in this case, maybe committing a type 2 error is not is probably maybe a little more consequential. Another way of thinking about that is when it comes to rain, type 1 error is, thinking, okay, it's gonna rain, so I'm gonna bring my umbrella, and then it doesn't rain. Okay, well, inconveniently now I have to carry my umbrella around. I guess that's slightly inconvenient. Type 2 error in this case is, oh, hey, there's a chance it's gonna rain, but hey, I don't think it is, so I'm just gonna not bring an umbrella. Then it ends up raining on you. So type 2 errors in this case, in the two examples I provided, tend to have a little more consequence. But when we talk about probability, remember, our alpha level, we measure alpha in terms of the probability of committing a type 1 error. We measure beta in this case is the probability of committing a type 2 error. So this is kind of a matrices to show you if we reject the null hypothesis, but there is no effect, we're committing a type 1 error. If we reject the null hypothesis and we make the correct decision when there is no effect. If we fail to reject the null and there is no effect, we made the right decision. But if we fail to reject and there is some kind of meaningful relationship going on there, then we've committed a type 2 error. And so these are those critical regions. Depending on alpha, zero point zero 0.05 is going to be 1.96 positive or negative, zero point zero 0.01 negative 2.58, and 2.58. So, we're getting really into the nitty gritty, but we're going one standard deviation, two standard deviation, three standard, we're moving further and further out into those critical regions, which is going to, it's going to shrink those critical regions you need for rejection or retaining the null hypothesis. All right, quick comprehension check. More true false. First one, a type 1 error is like convicting an innocent person in a jury trial. Second one, true false. A type 2 error is like convicting a guilty person in a jury trial. So go ahead and pause the video here, kind of work through that if you need to. And yeah, here we go. All right, first one is true. Innocence in the null hypothesis for a jury trial conviction is like rejecting the null hypothesis. And false, the second one is false. Convicting a guilty person is not an error, but an acquitting a guilty person would be more like a type 2 error. So convicting someone who is guilty, that's the correct decision. But if you acquit somebody who is guilty, that is a type 2 error. Okay, more about hypothesis testing. Again, we state our hypotheses, excuse me. We select our alpha level, locate the critical region, we compute the test statistic, make a probability-based decision about the null hypothesis. And how do we report those results? We're reporting a result is significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. So essentially, this is how we report rejecting the null hypothesis. Typically, you'll see this found in terms of a significant effect, reporting the test statistic, and also the p-value for the test statistic. So the size of the difference between the sample mean and large discrepancies tend to mean larger z-scores. Variability, we look at that. More variability of the scores means larger standard error, and the number of scores in the sample, larger our sample size in this case usually means smaller standard error. Some of the assumptions that go into hypothesis testing or especially with z-scores, we're talking about random sampling. We have independent observations. Our value of our standard deviation is unchanged by the treatment, and we have a normal distribution of our sampling. So the unit normal table, we can use that unit normal table we've used before. Okay. Let's take a look at a researcher uses hypothesis test to evaluate the null hypothesis that mean equals 80. Which combination of factors is most likely to result in rejecting the null hypothesis? So if you'll pause the video here, maybe think through it, write your answer down, and come back. It's going to be B, standard deviation of 5, and a n equals 50. If you go back a couple slides, some of those sampling. So, larger discrepancies, larger z-scores, variability. This one we're talking about smaller variability, and also the largest sample size. Those are things that are going to influence a hypothesis test. Okay, true, false. An effect that exists is more likely to be detected if n is large. True or false. Second one, true or false. An effect that exists is less likely to be detected if the standard deviation is large. Both are true. Sorry, I should have told you to pause the video. Hopefully, I didn't jump the gun too soon. Hopefully, you're in the habit now. You pause the video. True, a larger sample size produces a smaller standard error and thus a larger z-score. And true, a larger standard deviation increases the standard error and produces a smaller z-score. So you can kind of see how these different, measures of central tendency, sample size, variation, how those things can affect our results. Okay, so far we were looking at two-tailed hypothesis. Now we're going to take a look at one-tailed. Typically, the standard procedure for hypothesis testing is a two-tailed. We're looking at both tails, non-directional in terms of our hypothesis. We're just saying there's no difference or there is a difference. But we can also, if we have a more specific prediction, then we can talk about a one-tailed hypothesis, and we can talk about the specific direction of our treatment in this case. So when we have a specific direction of the treatment, we can predict it can then be incorporated into our hypothesis the way we phrase those hypotheses. So with a directional or one-tailed hypothesis test, the researcher is specifying either an increase or decrease. We're now saying what direction. Not only is there a difference, but we're predicting what direction the difference is likely to happen based on our treatment. So, maybe we're saying in this case, we have our mean, we have our standard error score. We might say now on our one-tailed test, we think our treatment group is going to improve, like they're going to have higher scores than our sample mean. So they need to be in this right-handed side tailed in order to reject the null hypothesis. So a one-tailed test allows us to reject the null hypothesis when there is a relatively smaller difference in the specified direction, because instead of dividing up the 0.05 in two tails, we now have it all in one tail. You have to have larger differences regardless of the direction with a two-tailed test, but now one-tailed test makes that a little bit easier, at least if you're on the one side of the tail. Two-tailed test should be used unless there is a strong justification for a directional prediction, though. So just FYI there. Okay, learning check. A researcher is predicting that a treatment will decrease scores if the treatment is evaluated using a directional hypothesis test. And the critical region for the test is it A, would be entirely in the right-hand tail of the distribution, B would be entirely in the left-hand tail, C would be divided equally between the two tails, or D cannot be identified without knowing the value of alpha. Go ahead and pause the video and write your answer down or jot it down. Keep it in your head, whatever you got to do. Okay, we're back. It is B, would be entirely in the left-hand side. So if you're making that prediction, that specific prediction that the scores will decrease, you're focusing on the left-hand side. If you said it would increase, you'd be on the right-hand side. All right, here's some quick practice. Make sure you understand the difference. Directional or non-directional. There is a difference in body weights with men weighing more than women. What do you think that is, directional or non-directional? Maybe take a stab at that. Write it down. Pause the video. Come back. That is non-directional. We just say there is a difference. Next one, women are better at concentrating on more than one thing at a time than men. Again, pause. If you think it's directional or non-directional, pause, write your answer down. Okay, that is a directional. We're saying women are going to perform better in this case. We're comparing men and women. We think women are going to score better. There is a relationship between studying and final exam score. Pause. Okay, that is a non-directional. We just say there's a relationship. We don't know if it's positive or negative. Next one, Sarah believes that as employees earn more money, they become less likely to leave an organization for a new job. Is that directional or non-directional? Pause the video. Come back when you think you have an answer. Correct answer is directional. We're adding value statements like more, better. Those are directional language versus, relationship or difference. Those are non-directional. Okay, here's a quick practice of what this might look like, and I'm just going to kind of walk through the steps just slowly and kind of help you see what goes into this. So suppose you believe that women over the age of 25 have less anxiety about going to the dentist than the average of 7.5 on the dental anxiety scale. You know the population standard deviation is 1.34. To test your hypothesis, you collect a random sample of 30 participants, all women over the age of 25. You measure them on the dental anxiety scale. You calculate a mean score of 6.8. So what is your statistical decision? Follow all the steps for hypothesis testing. Write your hypotheses, so be sure to pay attention to whether it's directional or non-directional. So you want to know if it's one-tailed or two-tailed. Make your statistical decision to reject or retain according to both the critical value rule and the p-value rule. In other words, be sure to find both the p-value and compare it to the alpha in addition to calculating your statistic, which I guess we haven't looked at p-value yet, but don't worry about that. So not going to go through that all again, but our null hypothesis in this case is there is no difference between the women over the age of 25 and our general population, the ones we sampled. Our null, or excuse me, our alternative is the women over 25 have less anxiety on the DAS scale than the population average. So in this case, we're talking about a directional, one-tailed, based on the language used here. So we're going to use the lower tail. We want to see if those scores are lower than the average. We are going to compare the sample mean of the population mean to the known population standard deviation. So we're looking at Z of X bar. That's that equation I showed you a while ago, but I think it's going to come up again here in just a minute. We set our alpha level to 0.05. So we're looking at anything that falls in this critical region here will allow us to reject this null hypothesis. So our value in that case is going to be minus 1.64. You can find that on your unit normal table. Sorry, I should have showed you how to use that, but that's where that value comes from. That's our rejection region, and this is our equation. Same thing I showed you earlier. Z of X bar is just using our mean, what we derived from our sample, comparing it to our population over our standard error of the mean equation. So in this case, we have 6.8. I'm just pulling this data from here. Minus 7.5. We know the population standard deviation is 1.34. We have 30 participants, so that's going to be that N. Just showing you where those numbers came from. Becomes minus 0.7 over 1.34 divided by 5.48. 0.7 minus 0.7 divided by 2.45 gives us negative 2.86. So that's going to fall. Our rejection region starts here at negative 1.64. Our Z of X bar in this case is going to be negative 2.86. So it's way off and to the left compared to our mean. We then look up our p-value. In this case, 2.86. The closest value is going to be somewhere between these two values here. So we can definitely reject the null. Women over 25 have significantly lower anxiety scores on the DAS, this dental anxiety score, compared to the rest of the population. So, anyways, that's just kind of showing you how to work through some of that stuff, like what the language might look like and how you might put all those steps together to come up with a decision. Okay. Some concerns now. Not only do we have to measure things about like whether it's statistically significant or not, we might also want to evaluate the effect of the treatment. So scientists also are concerned about hypothesis testing, focus on the test size, but we also want to look at things that besides just whether it's significant or not. We want to look at the magnitude of the treatment effect. We want to know how strongly the effect is happening beyond just whether it's producing a statistical significant effect or not. So in this case, we would look at Cohen's d, which measures the effect size simply and directly in a more standardized way. So the Cohen's d is taking our mean difference of the treatment minus no treatment divided by standard deviation, and just kind of a scale to go by in terms of measuring its magnitude. Values that are considered 0.2 at around 0.2 are considered small effect, like there is an effect happening, but small. 0.5 is considered a medium effect. Anything over 0.8 or greater is considered having a large effect. And so here's kind of what that might look like. You might have, two different Cohen's d in this case. We have d equals 0.15. We're comparing the distribution of scores on SAT scores before and after treatment. So this would be considered a small effect size, probably just barely kind of making that qualification of small. And you can even see the lack, you can see the difference. There's still a lot of overlap between the treatment group and the general population compared to an effect size of a 1, which is great. It's a very large effect, but there's not as nearly as much overlap. We're seeing much more different scores in terms of we're seeing better improvement on those scores. It's having a more noticeable effect beyond just a statistical significant effect. Okay. Let's see. Quick learning check. If increasing the sample size will also increase the effect size, is that true or false? And then second one, true or false, false, larger differences between the sample and population mean increase effect size. All right, pause the video here. First one is false. Sample size does not affect Cohen's d. Remember that equation, effect size or sample size does not take into effect. True, or second one is true. The mean difference is in the numerator of Cohen's d. So just go back to the equation to be able to answer both of those. There's also this idea of statistical power we have to take into consideration. Power of a statistical test is the probability the test will correctly reject a false null hypothesis. So it will detect a treatment effect if there is one that exists. So power really is just 1 minus b. In this case, we're really talking about b, where b or beta is the probability of a type 2 error. And this is estimated before starting your study, making certain assumptions about the factors that might influence power. So how do we calculate that? You sketch your distributions for the null and alternative hypotheses, locate the distribution. So you want to actually draw out those normal distributions, locate the critical region, compute your M statistic, compute the Z-score for the alternative distribution, and find power from there. So this is just kind of a demonstration. You have your null hypothesis, n equals 4. We're saying there's no difference. Alternative distribution, n equals 4 with an 8-point effect. And whether or not do we reject the null hypothesis. So looking at those critical regions. Increased power has an effect as effect size increases, so does power. Large sample size produce greater power. One-tailed test increases power compared to a two-tail. Things that decrease power, reducing your alpha level, going from 0.05 to 0.1 for 0.01, for example, making the test more stringent reduces your power. Using a two-tailed test decreases power. All right, so sample size, this is just showing how sample size could affect power for your hypothesis test. Different sample sizes is going to increase or decrease those rejection regions. Sample size, alternative distribution. Yeah, some graphs you can take a look at. I think these are also in your textbook too. Yep. Okay, quick learning check. The power of a statistical test is the probability of blank null hypothesis. Is it A, rejecting a true null hypothesis, B, supporting a true null hypothesis, C, rejecting a false null hypothesis, excuse me, or D, supporting a false null hypothesis? A false null hypothesis, null. That's a really weird one to say, that D. Sorry, that really threw me off there. All right, pause your video, come back when you think you have the answer. Yeah, it's C, rejecting a false null hypothesis. Next one, decide if each of the following statements is true or false. First one, true. Cohen's d is used because alone a hypothesis test does not measure the size of a treatment effect. True or false, lowering the alpha level from 0.05 to 0.01 will increase the power of your statistical test. Pause your video, come back when you think you have your answer. First one is true. Difference might be significant, but not of substantial size. Second one is false. It is less likely that HO will be rejected with a small alpha. All right, that's it for chapter 8. We will come back and look at t-tests in chapter 9, but that's just kind of a nice introduction to hypothesis testing. Please leave any questions or concerns you have. Otherwise, I'll see you on the other side for chapter 9. Take care. Peace.